welcome back. This is Unit 7.1, Properties of Solutions. We're going to be talking about different solutions and how scientists measure a solution. So in your textbook, this is pages 544 through 559. And in your workbook, if you have that with you, that's page 226 to 233. All right, so let's get right into it. Solution. What is the definition of a solution? Okay, a solution is a homogeneous, homogeneous, O-U-S. It's a homogeneous mixture. Okay, and there's two parts to a solution. There's the solute and the solvent. Now, usually the solvent is a liquid, and the solute is some kind of solid. But not always. Sometimes you can have another liquid as your solute. So, more technically speaking, the solvent is the part that does the dissolving. And the solute is the substance dissolved. Okay, so make sure you pause and you write this down, please. All right, so the process of dissolving, you may hear or see, like in your textbook, is called dissolution. Okay, so if you see that in a test question or a quiz question or something, just know dissolution means to be dissolved or the act of being dissolved. All right, so there are factors that affect the rate of dissolving. The rate, how fast. Okay, so remember, rate is how fast. Like, what is your rate of speed? That's how fast you're going in a vehicle. So factors that affect how fast something dissolves are surface area, temperature, and agitation. Now, I have a picture here that's going to help us keep these straight. So first of all, surface area. So if you look right down here in the bottom of this glass of tea, you see a sugar cube. Okay, and if you look over here, you'll see that the sugar is granulated, like not powdered, but granulated. So surface area means how much of the surface of these molecules are touching the liquid, because it's the liquid that does the dissolving. So if you have a sugar cube, the inside of that sugar cube is not touching any of the liquid. So only the surface of the sugar cube can be dissolved. So that's like maybe putting a jawbreaker into a glass of water. That's going to dissolve a lot slower, like several days, rather than taking and crushing it up in something and then putting the powder into a glass like this. And there is a pain reliever. Let me see if I can bring this up. Hold on just a second. I'm going to show you a picture of this. I don't know if you can see this. Yikes. Okay, that's really big. And this is just a quick Google search. There is a pain reliever called BC powder, and it works really, really quick. It says fast pain relief. That's because it is a aspirin that has been crushed up into a fine powder. See, it says 2 powders, and it's put in a little paper envelope, and this works so quickly because it's all crushed up. So your body doesn't have to like break that down. Let me get rid of this real quick. Your body doesn't have to dissolve that tablet in your stomach. It's already broken down into a powder form, so it can get into your bloodstream a lot quicker and give some relief from some pain. All right, so surface area. The more surface area that something has, the quicker it's going to dissolve. Okay, sugar cube versus granulated sugar. Okay, temperature. Temperature also affects how quickly something can dissolve. So we have here a cup of hot tea versus a glass of iced tea. Both of them have the same type of sugar, but the hot tea is going to dissolve the sugar a lot quicker than the cold tea. And sometimes maybe you've been to a restaurant and you've ordered sweet tea and they don't have sweet tea, but they do have sugar packets. And so they give that to you and it's just not the same. It just doesn't dissolve the same as when you put it in hot water. So when you're making sweet tea at home, you always warm up the water so that it can dissolve all the sugar. And you put the sugar in the warm water, and then that way it's there. When you add your ice, you don't have to worry about it. So temperature, the higher the temperature for most substances, now we're going to look at a graph in a minute and we're going to compare that. But for most substances, the higher the temperature of the solvent, the quicker the rate is going to be in dissolution. And the third factor that affects is agitation. So here, this is why you have the spoon here, because what agitation does is it stirs up the sugar so that the sugar particles can actually come in contact with new liquid that doesn't have as much stuff dissolved in it. Because let's look back here. I'm going to go back here. I'm going to show you what happens. So let's just say we have our sodium chloride salt that we're going to put down in some water to dissolve it. Well, water is a molecule that looks like this. It's a bent molecule, okay? And the oxygen here has a negative charge, and these two hydrogens have a positive charge. Okay, so remember, sodium is positive, chlorine is negative. So what happens is this water that has the negative end right here will come over here. And when this meets the sodium, which is a positive, it's attracted. So this will break apart. This water will actually make this sodium break apart. And then when this sodium breaks apart to be a sodium ion and it's positively charged, then a whole bunch of water molecules will surround it and it will orient or point its negative end toward the sodium and surround it like this. Okay? And vice versa with the chlorine, which is negative, now the water molecules will orient themselves, turn so that the positive end, the hydrogen end of the water, the positive end is facing the water molecule this way. I'm sorry, the chlorine ion. Like this. So when you stir this, what happens is it gets new, like for here, let's say that these water molecules were surrounding the sodium like this all around it, and we had some other sodium chloride, other salt crystals here. Well, these waters, because these are touching these, can't get to the sodium chloride. So when we stir it up and agitate it, this will float off this direction and expose this so that more of these water molecules can come in and attack that and rip these apart. So that's what stirring does. It just, you stir the pot and it gets new liquid, new solvent to come in contact with the solute. Okay. All right. Factors that affect if a solvent is going to be soluble. So here we're talking about, we're assuming that this is going to dissolve and we want to change the rate at which it dissolves. But factors that affect if it's going to dissolve, okay, those two factors are temperature and polarity. Now, as I mentioned before, if the temperature is really, really low, then things may not dissolve. We're going to see a chart about that here in just a second. And polarity just means you can think about it as the charge of the molecule, whole molecule as a whole. And we're going to talk about that after we talk about temperature. So here is a graph, and let's look at the X and Y axis. Let's analyze this. So the X axis is solubility, and this is grams of the solute per 100 grams of water. So if you take a beaker that has 100 grams of water in it, and this is what they did to get this chart. Okay, so it has 100 grams of water in it. How many grams of this compound can dissolve in that? And they tested it at certain temperatures. So 0 degrees Celsius, which is just freezing basically, 10 degrees, 20, all the way up to 100 on this graph. Okay. All right, so let's analyze these. Let's take salt, for example. So at 0 degrees Celsius, almost freezing, about 31 grams of salt can be dissolved in 100 grams of water. Now look, as we increase the temperature, this line ever so slightly starts going up. So there's not very much difference between 0 degrees and boiling, which is 100 degrees. At boiling, this can hold 40 grams of salt instead of 33 or 32. Okay, so it only goes up very, very slightly. Now, if we compare that to potassium nitrate now, at 0 degrees, potassium nitrate can hold 12, but look how steep this curve is, okay? So at 53 degrees, it can hold 100 grams of potassium nitrate. So this graph right here kind of relates to the coronavirus graph of people getting infected. What we want is to flatten out this curve of these people that need hospitalization and hospital care like ventilators. We want it to look like sodium chloride, where at this point in time, it's this many people that need to be in the hospital. And at this point in time, it's ever so slightly just a few more people. And that's why we have this stay at home order, so that we don't spread the virus and overwhelm the medical system. And if we did that, it's going to look more like the potassium nitrate. So here at this point in time, we have this many people, but if we go out and start hanging out at, restaurants or movie theaters or hanging out with our friends that have been exposed, then we're going to start exposing each other, and the number of people that are affected by the virus and need to be hospitalized is going to go way, way up, skyrocketing. So it'll look more like this curve. Okay. All right. So back to solubility. So if this graph tells us how much solute can be dissolved in 100 grams of water, what if, say, we had 20 degrees Celsius water and it can hold, what, 35 grams? What if we only put 32 grams? Or what if we only put 15 grams right here? So right here. Well, there's a word for that, and that's called unsaturated. So anything that falls below this line is unsaturated. That means that in this water, it could dissolve more sodium chloride, but we didn't put that much in there. We only put 15 grams of sodium chloride. So this line is called the line of saturation. So this is the most that the water could dissolve of sodium chloride at that temperature. So when it hits that temperature, it's saturated. So if you had some salt in water at 40 degrees and it was 36 grams of salt, when you put in another gram, it would not dissolve. It would just be at the bottom of the container, pardon me, just like this. So when you put it in, it wouldn't dissolve. It would just go to the bottom and just sit there. And it wouldn't matter how much you stirred. It wouldn't matter what you did. It would not dissolve because that liquid is saturated with the sodium chloride. Now, keep in mind, it's different for every compound that you want to dissolve in water. We're just talking about the sodium chloride here. Anything less than that 36 grams, and it could dissolve more, so that is said to be unsaturated. Now, there is a term called super saturated. And let's talk about that real quick. Super saturated means that there is theoretically more compound dissolved in the liquid than it can hold at a certain temperature. So the way we achieve a super saturated solution is, say here for the KNO3, we heat this KNO3 up to 55 degrees Celsius. When we heat the liquid up to 55 degrees Celsius, now we're going to add 100 grams of KNO3, and it's all going to dissolve because it's on the line of saturation. And then really, 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 really slowly, we're going to cool this down. We're going to cool it down. We're not going to bump it. We're going to leave it very, very still. We're going to cool it down to room temperature, which is about 23 degrees, about right here. So at 23 degrees, it can hold only about 31 grams. Okay, but remember, we dissolved 100 grams in it. So how many grams is actually dissolved that theoretically shouldn't be? Well, it's about 69 grams, right? 69 grams. Okay, so looking at this next illustration, here we have the KNO3 that's dissolved, and it's at room temperature now, and so it's holding 71 grams that it shouldn't be able to hold. Well, if you look at these forceps right here, right there, they're holding a little tiny crystal of KNO3, a very, very tiny crystal. Now, they're going to drop it in, and when they drop it in, it's going to hit the water, and it's going to give a base for these crystals to build on. So what happens is these crystals are very, very quickly. Now, this happens in a matter of like 5 seconds. It's like very quick. These crystals have this seed crystal here to build on, and so they start building crystals on it. And pretty soon, that 71 grams over here in this last picture has all crystallized around that seed crystal. Okay, and the practical application of that you may have seen is rock candy. So what the people who make rock candy do is they take and they dissolve lots and lots and lots of sugar at a high temperature. Now, they don't cook it, because if they start cooking it, then it's going to turn into more of a caramel. But they'll just dissolve it, and then they'll stop cooking it, And then really they'll put a stick like this down into the beaker or whatever they're making it in. So you have this stick that's down in here. But before they put the stick down in there, they'll get the end of it wet just a little bit, and they'll roll it around in some regular sugar. Then they'll put the stick down in there. And pretty soon, these big, huge sugar crystals will start growing on this. And for rock candy, it takes a little while, like maybe overnight or a couple of days. And they'll keep growing on the outside of this until you get this. Now, the way they get the different colors is by using food coloring in the liquid, probably a powder coloring. And so that coloring gets trapped between the crystals, and then you can see it. And they'll also put different flavors in there. Okay, so we talked about saturation. We analyzed this graph. One thing that I do want to point out, if you didn't notice it before, is look here. Ce2SO4 cesium sulfate. This is an exception to the rule. Okay. Now, remember just a moment ago, I said for most things, as you increase the temperature, the amount that you can dissolve in the water is going to increase. So if we look at all of these other lines, they have a positive slope. They're sloping upwards, right? But for a few compounds, the higher the temperature, the less that can be dissolved. And that's the case here for cesium sulfate, so that's why this is a negative slope. Now, that's also true for gases like carbon dioxide. The higher the temperature, the less gases can dissolve. So my dad used to have in his backyard a koi pond, and a koi, K-O-I, is a Japanese fish. And in his koi pond during the summer here in Texas, when it gets really, really hot, the surface of the koi pond couldn't dissolve enough oxygen so that the fish could breathe. So what he used to have to do is take milk jugs and put milk jugs in his freezer. He had an extra freezer in the garage, and he would freeze these, and he would put these milk jugs in the koi pond and just float them in the koi pond so that it would cool the water down enough so that more of this oxygen could dissolve in the koi pond and the fish could breathe. Okay? So during the summer when the water was warm, it couldn't absorb enough oxygen to support the fish that he had in the pond. Okay, and oxygen is a gas. So maybe from that story you can remember that for the test. All right, so let's talk about polarity. Polarity is, remember what I said a while ago, a charge that's on a molecule. So if we have like water, let me show you what I mean by charge. And it's only a very slightly partial charge. So here we have the two hydrogens that are on water, and then we have the oxygen. Now we know oxygens are negative and hydrogens are positive. Well, when we take this molecule and we put it together on paper like this, we know that the charge of oxygen is a -2 and the charge of the hydrogen is a +1. Now we have two of these hydrogens, so this total charge is a +2. I remember when I said when we make compounds, we have to make sure this charge equals 0. Okay, and so this whole molecule as a whole, the charge is neutral. But because of the way that water is shaped, with the two hydrogens poking up behind the water, this gives water, the shape of it gives it a slightly charged configuration. So because these two hydrogens point backwards like this side has a slight positive charge. Okay, and this is the lowercase Greek letter delta. And this side has a slight negative charge. Okay, and it's just because of the way that it's shaped, but the overall molecule is neutral. So there are a lot of other molecules like that. For example, NH3. NH3 has a slightly positive end and a negative end. SO2, H2S, and C2H6O, those are just some examples. These are called polar molecules. Now, let's contrast that with non-polar molecules. So let's take carbon dioxide. Well, if we look at carbon dioxide, and if we think back to when we were drawing these shapes, carbon dioxide looks like this. So because of the shape of this molecule, the orientation, you don't have any one side that's more positive or more negative than the other. So the charge is here because it's linear and not bent like water. These charges are evenly distributed across the molecule. So this is called nonpolar. It doesn't have poles. Okay, it's even. And so when we talk about if something is going to dissolve, then we remember like dissolves like. So what that means is polar molecules, polar solvents will dissolve polar solutes. So NaCl. NaCl is polar. Okay? That's why it will dissolve in water. Okay? But carbon dioxide is nonpolar. C6H6 is nonpolar. CH4 is nonpolar, and C2H4 is nonpolar. Usually a lot of your organic molecules that contain carbon, hydrogen, oxygen, and nitrogen together are organic or nonpolar molecules. Okay, so just remember like dissolves like. And the next question you're going to ask is, well, if I see this on the test, how am I going to know? How am I going to remember that this is polar or nonpolar? It will tell you on a test. It will say, if you have a polar molecule of SO2, and it'll say polar molecule, will it dissolve in water? Well, we have to remember that water is polar. Okay, so probably that's the only one that you're going to have to remember. And the answer is yes, because they're both polar. But if it says you have a nonpolar molecule of methane, will that dissolve in water? Well, it says nonpolar molecule of methane. Will that dissolve in water? Well, we know that water is polar. So polar, nonpolar do not dissolve. Okay, so like dissolves like. Polar solvents dissolve polar solutes. Nonpolar solvents will dissolve nonpolar solutes. Okay? Okay, so that's enough about just the concept of dissolving and dissolution. So when you have a certain amount of a solute dissolved in a solvent, scientists measure that. Okay? And of course, in chemistry, we measure that as well. So the amount of solute dissolved in the solvent, okay, is what we call concentration. How concentrated is that? Okay, it's called concentration. And the unit we use to measure concentration is called molarity. Molarity, and this is going to be a capital M. Okay. And so the formula for molarity is equal to the number of moles of solute divided by the liters of solvent. Okay, so we have, if we were going to take and just make the variables, molarity is equal to N, because remember, N is the variable for moles, divided by liters. Okay, so this has to be in liters, this has to be in moles. Now, if you remember back to the first of the year, we talked about the triangle, the density triangle. Just let me review you on that real quick. We drew a triangle like this. Okay, and we put a T inside of it. We said that density is mass over volume. Well, because it has three variables, we can do that. We could do the same thing now for the formula for molarity. So some of these questions that you're going to have on your homework are going to ask you about the formula for molarity. Like one question may say, what is the concentration I just wanted to write concentration there for you so that you know that molarity is concentration. So when you hear that word concentration, it's asking for the molarity. What is the concentration of a solution that contains this many moles and this dissolved in this many liters? Okay, so we can use this density triangle to help us figure that out. So this, if we cover this up, so remember to use this, we cover it up, and whatever's left, that's what we want to solve for. Whatever's left is your formula, so it's N divided by L. Okay, so some questions are going to say, if you have a concentration of, and it'll give you, I don't know, a number 1.1 molar, and you have a volume of 1 liter, how many moles are dissolved? Okay, so we're looking for moles, so cover that up. Okay, the formula is molarity. When they're side by side like this, it's multiply, so it's molarity times liters. So it'll tell you the formula. And then another question is going to say you have this molarity and you have the number of moles. How much liquid did we have? So cover up, we're looking for liquid. Let me fix that. We're looking for liquid, so it's going to be moles divided by the molarity. Okay, so remember, that's how you use that density triangle. Okay. All right, so let's look at a sample question. Okay, so pause here, write down the sample question in your notes. Because remember, on these quizzes, you're able to use your notes. Okay, find the molarity. Okay, so molarity is what we're looking for. So I'm going to list out. I'm going to still use glue, so I'm going to start listing out as I read. Okay, find the molarity. So that's the question mark, molarity. If, okay, so 0.25 moles of CaCl is dissolved to prepare a 1.2 liter solution. Okay, so find the molarity. That's what we want. All right, so molarity is my question mark. 0.25 moles okay, that's my N. That's the number of moles. Okay, and 1.20 liters, that's my volume. All right, so here's my density triangle. Okay, so the next step is to glues. I'm going to write glues up here. So we circled our givens. Okay, we listed them out. We underlined what we're looking for. Now we get our equation. So if we use the density triangle, M, N, L, and L or V. V is volume. It's in the unit of liters. So sometimes I'll write a V here. Sometimes I'll write a L. Most of the time I write a L. So we're looking for molarity. So I'm going to cover that up. So it's going to be moles divided by liters. All right, so there's our equation. So now we substitute and solve. That's the S. So what am I going to substitute in for moles? 0.25 moles divided by, what am I substituting in here? 1.20 liters. Okay, so if you want to grab your calculator, 0.25 divided by 1.20. Okay, that's going to give us a 0.2083. The unit for that is capital M, molarity, capital M. All right, so significant digits. Here we have 3. Here we have 3. We're multiplying and dividing, so the rule says you take the least number of significant digits. I'm sorry, this is not 3. This is 2 because it has a leading 0. Okay, so be careful about that. I made that mistake. I don't want you to make that mistake. Leading 0, this is 2. This is 3. This has a trailing 0. We have a decimal here, so that trailing 0 counts as significant. So our answer, the least, is 2. So here's 1, 2. Our third significant digit is the 8. So that's greater than 5. So it's going to bump this 1 before it up 1. So our final answer is going to be 0.21 molarity. Okay. So that's how we work that out. All right, let's do another one. Find the total volume of a 0.30 molar solution if 0.72 moles of KBr are dissolved. Okay, so find the total volume. That's our unknown. So let's list these out. So question mark is going to be the volume. Okay, 0.30 molar KBr. So our capital M is going to be 0.30 molar. Let me make that point bigger. All right. If 0.72 moles of KBr are used. So our N is equal to 0.72 moles. All right, let's get our equation. Molarity is equal to moles over liters. So we're looking for liters. We're looking for the volume. So it's going to be moles over molarity. So let's substitute in how many moles. 0.72 divided by molarity, which is 0.30. Okay, so grab your calculators again. 0.72 divided by 0.3. It's going to be 2.40 liters, because moles divided by molarity is going to leave liters. All right, sig figs, we have 2 here. We have 2 here. So our answer is going to have 2. So this right now has 3 because we have a decimal, this 0 is significant. So we're going to drop that off. Our final answer is going to be 2.4 liters. All right. Find the mass of NaCl needed to prepare 2.5 liters of a 0.15 molar solution. Okay, so we want to find the mass of NaCl. So we're going to list this out. So we want to know the mass. Okay, and mass is in grams. All right, 2.5 liters. So our volume is equal to 2.50 liters. And our molarity, because it's capital M, is equal to 0.15. Well, it's not really clear to me how I'm going to solve this, but that's okay because I don't have a formula yet. So molarity is equal to moles over liters. Well, I have liters, right? And I have molarity. So I must be looking for moles. Oh yeah, moles are related to mass. All right, so remember on your mole map, we have moles here. We have grams here. So we can go from moles to grams by using the molar mass. All right, so that's how we're going to get grams. We're going to solve for moles and then convert it to grams. All right, so we're looking for moles here. So our formula is molarity times liters. Okay, make sure this is in liters. It is. Sometimes they're sneaky and they give you milliliters. So make sure it's in liters. So we have 0.15 molarity times 2.50 liters. Okay, and that's going to give us moles. All right, so 0.15 times 2.5. All right, that's going to be 0.375 moles. And this is moles of NaCl. All right, so we're going to use this and we're going to convert. So 0.375 moles. Go ahead and write my E of NaCl. Okay, and we're going to put that over 1. All right, we're going to multiply it by a conversion factor. What do I want to get rid of? Moles of NaCl. So I'm going to put that on the bottom. What am I trying to convert it to? Grams of NaCl. So that goes on the top. All right, so now we need to put in numbers. Well, we need the molar mass of NaCl. So 1 mole of NaCl. Okay, remember molar mass. You add up the masses from the periodic table. So let's go ahead and pull up our reference sheet. All right, so here's our reference sheet. Sodium is 22.99 right here. Chlorine is 35.45. So 22.99. And we only have one. We have 1 chlorine, which is 35.45. So add those together. That's going to give us 58.44. So 1 mole of salt is 58.44 grams. Okay, cancel what you can cancel. We can cancel moles with moles. That's going to leave us with grams. Find the mass. So that's the unit we want, grams. So we can stop here. We don't have to do any more conversion factors. We can multiply this out. So 0.375 times 58.44. That's going to equal 21.915 grams of NaCl. However, we need to check our sig figs. So we have 3 here and 2 here. So we just need 2 sig figs. So this is 1, 2. So the 9 is going to tell us if we round or raise or not raise. And it is going to bump the 1 in front of it to a 2. So we have 22 grams of NaCl as our final answer. Okay. All right. So we've worked 3 problems. Our first problem, we're trying to find molarity. Our second problem, we switched and we were trying to find the volume. And then in our third problem, we found the moles, and then we had to convert that moles to grams because that's what the question was asking for. So we've seen an example for each one of these. So let's talk about dilution. Dilution is a part of concentration because sometimes if we have a certain concentration, like if we have a certain amount of salt that is dissolved in the water, we have a certain concentration. And what if we don't want that concentration? What if we want it to be what we call watered down? Then we're going to add more water to that, and the concentration then is going to go down. Okay, so this is like the orange juice that you buy at the grocery store that comes in a can in the freezer section. You take that can, it's very, very, very concentrated orange juice, and then you put that into your pitcher, whatever you're going to make it in. Then it tells you to add 3 cans of water to that. Okay, so what you're doing is you're diluting that concentrated orange juice to the drinkable solution, the drinkable concentration. Okay? All right, and of course, since this is chemistry, we have a formula to figure that out. It's M1V1 is equal to M2V2, where M is molarity and V is volume. So remember these ones and these twos, okay, 1 is before and 2 is after, or initial, the beginning, and final. Okay. So we have a situation where we have a before and after. Like the orange juice, we have that canned orange juice at a certain concentration. Okay, it's very concentrated. Then we add water to it. Okay, in the pitcher, okay, we've added in water, and so now it's got a different concentration. So we have a before and after situation. Okay, so again, the formula for dilution is M1V1 is equal to M2V2. So let's look how we use that. It says find the volume of a 3.2 molar HBr stock solution. So when you see that word stock, that means that it's a 1. It's the beginning. Your stock, like the stock at the store, when they open up the store in the morning, at the store, the shelves have been stocked. So they have a beginning number of items. And then as the day goes on and people buy them, then it's lowering the amount of stock they have left available. Required to prepare 150 milliliters of a 0.4 molar solution. Okay, so it says find the volume. So we're going to be looking for a V. We don't know which V yet. We're going to figure that out, but we're going to look for the V. All right, so let's list this out. So we have a 3.2 molar solution, that's molarity, and it's a stock solution. So right off the bat, you can figure that that's going to be a 1. Okay, so remember, that's a key word in these problems, a stock solution. If you see that, you can automatically put a 1 there. That's a stock. Required to prepare. All right, so this is a future. This is to prepare. That's future tense. A 150 milliliters. Okay, so that's going to be a V2 because it's something that's going to happen in the future. We're going to prepare this. And 0.40 molar. Okay, so that's molarity. And if this is of this, then this is the concentration of the M2. So if we can look at this, we see that we're going to be solving for V1 because that's what's missing. We have a V1 and a V2, M1 and M2. All right, so there we go. We know we're solving for V1. So let's write V1 is equal to M1 V1 is equal to M2 V2. All right, and just like when we solve for gases, we're solving for V1. So I'm going to put a box around that, and that locks it down. I can't move it. So in order to get it on the equal sign by itself, I have to move the M1. All right, so for multiplying here, when we drag it across the equal sign, it makes it go to the bottom. Okay, so there's your formula. So V1, so what we're looking for is M2 V2 over M1. Okay, so now we can just start plugging in. What are we going to plug in for M2? 0.40 molar. V2, 150 milliliters. All right, so be very careful. Remember I told you a while ago, sometimes they're tricky and they throw in milliliters here. It has to be in liters. So 150 milliliters, an easy way to change that is by moving your decimal 3 places to the left, 1, 2, 3. So it's going to be 0.150 liters. So 0.150 liters over molarity 1 is 3.2. Okay. All right, so let's look at this. We can cancel the 2 molarities because one's on top and one's on bottom. That's going to leave liters as your unit. And look at that. We're solving for volume. Liters is a volume. So we have the right formula. All right, so let's go ahead and plug this into your calculators. 0.40 times 0.150 divided by 3.2 is 0.01875. All right, so sig figs, right here is 2 sig figs. Right here is 2 sig figs. Right here is 2 sig figs, so it looks like 2 sig figs. Now remember, this 0 is leading. It is not significant. It is not a significant digit. So our first significant digit is this one. So that's 1. 2. So now we're going to look at this to see if we round. A 7 does round to 8. So our final answer is going to be 0.019 liters. All right. All right. What is the volume of a 4.2 molar solution? So go ahead and write this down. I'm sorry, I'll pause here and let you write this down. All right. What is the volume of a 4.2 molar solution of sodium bicarbonate? This is the bicarbonate polyatomic ion. So it's sodium bicarbonate are needed to make 1 liter of a 2.1 molar solution. So what is the volume? Okay, so we're looking for volume. We don't know that. Of a 4.2 molar solution, all right, so that's going to be an M, of sodium bicarbonate are needed to make, all right, so to make, to prepare, to make, that's a future tense. So we have 1.0 liters, that's a volume, and it's to make, future, so that's going to be 2. That's what we're going to be ending with. 2.1 molar, that's a molarity, and that 2.1 goes with the 1 liter of a, so these go together. So this is the concentration, this is the volume. All right, so this must mean that's an M1 and that's a V1. What is the volume of a 4.2 molar solution that's needed to make this? All right, so M1 V1 is equal to M2 V2. We're looking for V1 again, so we're going to lock that down. We're going to move the M1 down here. There's our formula. So now we can plug in M2, 2.1 molar, times V2. This is in liters this time, 1.0 liters over M1, 4.2 molar. Okay, molars can cancel, leaving us liters as our unit for our answer. So pick up your calculators, 2.1 times 1.0 divided by 4.2. That's going to give us a 0.5. All right, so how many sig figs do we need? There's 2 here, 2 here, 2 here. So we're going to need 2. This is only 1. I can fix that real quick just by adding a 0 there. So 0.50 liters is our final answer. All right, and that looks like it's it. That's it. So today, in these notes, we've learned about volume. We learned about solutions. What is a solution? How solutions are made. There's 2 parts to a solution. There's the solute and the solvent. We talked about the factors that affect the rate of dissolving. We talked about the factors that affect if something is going to dissolve. And we looked at a graph and analyzed a graph of temperature versus how much something dissolves. We called that saturated, unsaturated, or supersaturated. Okay, we looked at an example of supersaturation. Okay, we talked about polarity, like dissolves like, polar dissolves polar, nonpolar dissolves nonpolar. And we started looking at the mathematical formulas used to calculate concentration, which is molarity. It's called molarity, moles over volume. Okay, we did 3 examples, and then we talked about dilution, where we take that concentration and we add more solvent to dilute it. We looked at the formula for that, M1V1 equal M2V2. We worked out a couple of problems. All right, so you have your homework sheet. Work on those problems. And remember, at the bottom, there's this thumb that points upward. That's called the like. Slap that like button right across the face. Click on subscribe. Click on notify so you know when I put up these other videos. And we'll see you later.